Hey you guys, we are going to pick up where we left off in class looking at the integrated rate laws. So for integrated rate laws, we're looking at the change in concentration with time. And the graphs all look a little bit different depending on what order of reaction you have. So we did talk about zero order. Remember, a zero order reaction is going to be independent of the concentration. So as the concentration decreases, the rate is going to stay the same. So that is the blue line in our graph here. And so when this happens, we can find the slope and we can write an equation of the line. And what happens is the rate is equal to that change in concentration over the change in time. This is our slope. And in this case, it's a negative slope. And that is going to be our K value. And K is the rate law constant, like we calculated from our data sets. So we've got, this is our Y equals MX plus B format. So that's a zero order process. We see here the red one, the first order process, is not a straight line. So we need to integrate it. We need to get it to a straight line in order to find that K value. So when we do that, we end up graphing time on the x-axis again, but then it is the natural log of the concentration. So this is the Y equals MX plus B format as well. So negative K is going to be our slope. So we're able to find the rate law constant, again, from the slope of our line. So a graph is going to look like this, okay? We can use the equation of a line from a first order process to predict either the time that we'll reach a certain concentration or after a certain amount of time what our concentration will be. So for this one, the first order reaction A to B has a constant value of 8 seconds to the negative 1. So if our initial concentration is 0.500 molar, how long will it take to reach a concentration? And this is going to be at a specific time, that's what we're looking for, to reach 0.2 molar. So we're going to plug in what we know. So we know the concentration at a specific time. So we're going to take the natural log of, that's our 0.200. We know our K value, so negative 8. Time is what we're looking for because we want to know how long will it take. So what time will we be at? And then our intercept is our initial concentration. So ln of 0.550. So I've got my calculator handy here. I did have a calculator. Here we go. So I'm going to do my math here. So do it with me. We want to make sure that using your calculator is not where you are going to have issues. And these are not my final answers, so I am going to keep decimals. And then the natural log of 0.500 is a negative value, so I'm going to do minus 0.69314. Okay, so I want to solve for t, so I'm going to get rid of my 69314. Negative 1.6094 plus 0.69314. So I've got negative 0.91626, negative 8t. So to get t by itself, I'm going to divide by negative 8. And we get a time of 0.11. Got 3 sig figs, so 115 seconds, which when we're talking about reactions, less than a second makes sense for a change in concentration, especially one that is pretty fast here. Okay, so let's look at another example. So this is the same kind of idea. So I want you guys to try this. Stop the video, do it in your notes packet, and then check your answer. Okay, I got 0.246 seconds. So our K value is less. We're going a little bit further with our molarity, so it makes sense to me that it would take a little bit longer. So check out the work if you had any issues. Just be careful with your positive and your negative signs here. So So let's talk a little bit more about a first order process. So when we look at the process of converting methyl isonitrile to acetonitrile, so we've got CH3NC to CH3CN. So what's happening if we're looking is that our nitrogen and carbon, as far as the structure goes, have kind of swapped places in this reaction. We gathered the data for this, or someone gathered the data for this at 198.9 degrees Celsius, and this is the graph that they found. So from this graph, because it's not a straight line, we know for sure it's not zero order. Okay, if it was zero order, we would see just a straight decrease because it doesn't matter what the concentration is. So because we didn't see that, we know that this is not a zero order, okay? So now we need to decide what order it is, and so to do that, we're going to kind of change our data. So we are going to find the natural log, and in this case we measured pressure to tell how much we had, and we're going to graph that. So we went from just the pressure of the CH3NC, which is a way that we can measure concentration of a gas, and we converted it into the natural log. And when we did that, we did find a straight line. So when the natural log of the pressure is plotted as a function of time, we did get a straight line. This tells us that it is a first order reaction. Yay! Okay, so the process is first order. If we wanted to find the rate constant, the K value, we would find the slope. So when we did that, or when they did that, they calculated this to be the rate constant, and now we can predict the concentration at many different times. So a second order process would still not look straight. So concentration versus time would not be straight. Natural log versus time would not be straight. And so we need to integrate it in a different way. And what we end up doing is 1 over the concentration. So this is our integrated rate law for a second order process, where y is 1 over the concentration at a specific time. M and K are the same, so our slope is our rate constant. X is still time, like in all of ours, and then the y-intercept is 1 over the initial concentration. So if we were going to graph this, we would be graphing time, and then our y-axis would be 1 over the concentration of our substance. And what we're going to find is this is actually going to be a positive slope, which is why our slope is equal to K. Where in the other two, we saw a negative slope, meaning that our slope was equal to negative K. Okay, so if the process is second order in A, the 1 over the concentration versus time graph yields a straight line, slope is K. So that's what we just said on the previous slide. So if we look at this data, we would see the decomposition of the NO2 at 300 degrees Celsius is described by this data. So we collected time data, and then we measured the concentration of NO2. It's a reactant, so it doesn't surprise me that it goes down. If we look here, the intervals are not equal, so we know that it wouldn't be a straight line. So if I did 0.01 minus 0.00787. This one changes by 0.00213. 0.649 minus, minus 0.00649. This one changed by 0.00138. The next one changes by 0.00168. So we can see that that is changing. So if those changes were the same, because our timed interval is the same, it would have a constant slope, but it doesn't. So we know it's not zero order. Okay, so we can see that just from our data. And when I graphed it, so I graphed, we could see Next, if we plot the natural log of that concentration versus time, we get this graph here. So we have converted all of our concentrations into the natural log of concentration, and we see that it is also, so we can see that this is also not a straight line. It's better, but it still has a curve in it. So if it was a straight line, we would expect something like that, and we can see that at the end it deviates. So it is also not a first order process. So we need to keep going through the list. And when we graph 1 over the concentration, we end up with a straight line. So we see that we are going up in equal intervals along the process here. So this tells us, the straight line with 1 over the concentration versus time tells me that this is a second order process. Okay. So if we were given data, we could look at that data and calculate kind of that change in over the certain time intervals to make sure that this actually matches up. So you would be able to find this either from graphing the data or from doing some of those simple kind of comparisons.